Welcome back, Cat 5 class. So now we're going to continue on with Chapter 7, Part 2, Dimensioning. And just a reminder, this will be done by hand, or if you can sketch using some type of software on your computer, go for it. We're not using AutoCAD for this chapter. That'll be in the next chapter. Chapter 8 will be dimensioning using AutoCAD. And there is no new assignment for Chapter 7. Continue working on the previous handout for Chapter 7, Part 1. All right, so now let's talk about standards. Next slide. Standards. So we have to follow standards when it comes to creating drawings, whether it's automotive, architectural, aerospace, machine shops, metal forming shops. We have to follow a standard when creating our drawings. So these groups come up with standards on what sheet sizes to use, how to set up our title block and border, what to include in a title block, what type of lines to use for center lines, hidden lines, for example. Also what text heights to use, what arrowhead size to use. So let's go ahead and go over some of these groups. We have the ANSI group, which is the American National Standards Institute. We have the ASME group, American Society of Mechanical Engineers, and we have the ISO group, the International Standards Organization. So these groups get together on their own, and they're made up of professionals, sometimes retired engineers or retired professors, and they come up with the standards that we follow. So about roughly every 10 years, they'll come up with a new version of their standards. They're constantly updating their standards. And pretty much American standards and international standards. Also a group that I did not list here, we have Japanese standards. So pretty much they're all falling in line, coming together, almost coming up with very similar standards that we can all follow. So if you ever look at a drawing, look in the title block. Typically you'll see an ASME standards 1994, for example. That's the standards that were followed when that drawing was created. We do have updated standards. So anytime you create a drawing, you do list which standard you're following and what year those standards came out. Next slide. Okay, counterbore holes. We did mention them earlier in the previous lecture when we were talking about symbols. Okay, a counterbore hole is basically a small diameter hole. So you drill a small hole through a block. So here we have the smaller diameter hole. And then you follow it with a larger drill with a larger diameter hole. And it doesn't go as deep as the first one. So the result is a counterbore hole. So a little small diameter hole followed by a larger diameter hole with a smaller depth. Okay, so how do we call out a counterbore hole? Keep in mind that if you're looking at an old drawing, you'll see the word counterbore or C-bore. But now we use the counterbore symbol. So earlier we talked about symbols in the last lecture. Okay, so using a leader, and you want the text floating towards the top and the leader pointing down and the arrowhead pointing towards the center. Note that the arrowhead is pointing to the large circle, but it's also going to include the smaller circle. Now, even though we're pointing to the large diameter hole, we first call out the small diameter. So here we have a diameter of 10 units. So that's for the small hole, followed by a counterbore hole, right? So now we have a diameter of 20 for the large circle, the larger hole, with a depth of 15 units. So the depth of the large diameter hole is 15 units. Now note that we don't have a depth for the first hole, the small diameter. If no depth is called out for the first hole, the small hole, then you can assume it goes all the way through. Okay, if you want, and in old drawings you would write through, THRU, but pretty much you can assume it and just leave it out. Okay, next slide. Okay, so in this example it's the same as the previous slide, except the depth is not included. We still have the diameter 10 size hole, followed by the larger diameter hole of 20 units. Now, you will encounter situations where the plate, whether it's aluminum or steel, when you drill through it, You need to have enough material so when you place a bolt in here, typically you'll have this plate bolt onto another plate and you'll have a bolt in here. And when you tighten it to a certain torque, it's going to compress this material, whether it's uh, aluminum, steel, or rubber, and you want to have enough material so it doesn't crush. So instead of giving a depth, you want to give this dimension. So here we're saying that the length of 25 millimeters or 25 units is a lot more important than this depth. So you want enough material to handle the stresses when you bolt this down to another plate. Again, this is rare, but you do encounter this when dealing with thin plates. Next slide. So what is a counterbore hole used for? Typically it's used to hide the head of a bolt. Now, if you did not have a counterbore hole, then the head of the bolt would be sticking out. And typically it's not a problem if a head of a bolt is sticking out, but if you're going to have parts or movement going on top, parts sliding along the top, or parts bolting onto this plate on the top, or maybe even a human movement over the top, and you don't want somebody either hitting the head of the bolt or somebody accidentally hitting the head of the bolt. So what you do is you do a counterbore hole to hide the bolt of the head. And typically you want the head to be slightly below the top surface of the plate. And here's another example of a counterbore hole. The head of this bolt is slightly even lower. You don't want it flush. If possible, just make it slightly lower than the top of the plate. And typically a plate will bolt on to another plate. So typically you'll have another plate that it bolts onto. And the hole here will have threads. So you'll be able to clamp down the top plate onto this new lower plate by using the bolt. Okay, next slide. Sometimes you have to drill a hole, a counterbore hole, on a plate that doesn't have a flat top surface instead of has a contoured surface or maybe a rough surface. But you definitely want to drill the hole perpendicular to the base. Now, since it's hard to dimension to this rough surface, instead of using a depth for the counterbore diameter 20 hole, the large diameter hole, instead we'll dimension it from the base to the bottom of the counterbore hole, in this case 10 units. So now let's take a look at an example of where do you see this type of counterbore hole with a non-flat surface. Next slide. So here we have a water pump, an aluminum water pump for a Chevy big block, old Chevy big block. So when it comes to water pumps like this, instead of having to machine this from scratch from a block of aluminum, it's easier if you pour it into a mold. So this would be casting. And when you pull it out of the mold, you're going to have a rough surface, which comes from the mold after hundreds and thousands of parts have been made. You'll have a rough surface on the mold. And once you come up with a rough mold, or I should say rough shape from the mold, then you can go ahead and do some machining. You can machine the hole, for example, here where the water hose attaches to. You can machine the bottom where you have this foot, and you have another foot here. You machine it so these two surfaces are parallel and coplanar, and then you can mount to the front of the engine block, and you want a nice seal. You don't want anything to leak as far as water coolant. So the bottom of these 2 feet you will machine so you have a nice smooth surface, parallel and coplanar to each other. And also you want the bolts, when you bolt it onto the engine block, you want it to go in perpendicular to the engine block. So you're going to come in and machine these surfaces. These are referred to as spot faces. So before they were machined, you had a contoured surface here. So you come in and you drill your first hole, then you come in with your second hole, counterbore hole, and you come in and drill, and it's going to remove some of that rough surface with contours. So you're guaranteed to have this surface parallel to the base. Same thing with the other four. You have the top surface of the counterbore hole parallel to the base. That'll guarantee that the bolt will go in perpendicular. When you bolt it onto the engine block, you don't want this surface to be at a different angle, causing stress on the head of the bolt and causing a twist which may snap the head off of the bolt. So here we want parallelism between the counterbore holes and the base, and it'll be mounted onto the front of an engine block. Okay, next slide. Okay, now we're looking at a countersunk hole. So just like before, we come in and drill the hole, and then we come in and chamfer the edge, so you end up with the conic shape. Okay, so first you come in, drill a hole, and then with the second operation you'll drill around the top, and it'll give you a conic shape of a cone. Okay, so this is how we call out a countersunk hole. Okay, so even though it's pointing to the large circle, you actually first call out the small diameter hole. So the small diameter, it's 10 units. The depth from the surface, where you break the surface, to where the cylinder shape ends is 30 units. Okay, that's the depth. And now we have the countersunk hole, so that's when you come in and do the chamfer on the edge. And that's a diameter of 20. So the large circle has a diameter of 20, and it's created with a 90-degree angle or 90-degree chamfer. Now the 90 degrees is not from here to here. The 90 degrees is actually from here to here. Okay, so that's 90 degrees. Okay, so 90-degree angle, so it's 45 from the center to this face, 45 from the center axis line to this face. Okay, so for a total of 90 degrees. So that's how we define our countersunk hole. By the way, the most common angles to use for a countersunk hole is 82 degrees. So stress engineers have come up with these numbers. These are the good numbers to use, 82 degrees. And we also have 100 degrees when you're dealing with thin materials, like in aerospace, you're dealing with the thin sheet metal, typically aluminum metal. And then we also have the 90-degree angle. So these are the most common angles you'll see on a countersunk hole. 82 degrees is the most common one. Next slide. Okay, so what do we use a countersunk hole for? We use it to accommodate what's called a flathead screw. And we want the same angle for the head to match the wall of the countersunk hole. Notice there's clearance, so the diameter of the hole is a little bit larger than the actual bolt. And then we chamfered it around at the same angle as the flathead screw that we're going to use. Next slide. One thing that's very common, whether it's at the tip of a screw, a bolt, or a dowel pin, is just a cylinder, which typically is used for locating parts together. Okay, so typically we'll put a chamfer at the edge. So for example, here we have a chamfer of 2 by 45 degrees. So the 2 tells us that if you go to the intersection point between the horizontal and the vertical, you have a distance of 2 units, or in this case 2 millimeters, and the angle is at 45 degrees. So that's one way of calling it out, 2 by 45, or you'll get the same result if you call it out as 2 by 2. So from this imaginary intersection point to here is 2 units, back to the intersection point to this point is also 2 units. So you can call it out either way. Either you can say 2 by 45 degree chamfer or 2 by 2. You end up with the same result. I want you to note that there's a space, 2 space by space 45 degrees. Or again, you can use 2 space by space 2 units. Okay, so that's how you call out what's referred to as a chamfer. And by putting a chamfer at the edge of a cylinder, a bolt, it's easier to line it up when you're ready to insert it into a hole or a tapped hole. That's a hole with threads. A long way of calling out a chamfer is what you see here on the right. So on the left, this is the simple way of calling out a chamfer. If you want to call it out the long way, instead of calling out this chamfer as a 3x45, which is a lot easier, okay, we could have called it out like this one with the leader and called it out 3x45. That's one option. If you have the room, then if you want, you can do it the long way by calling out the angle, 45 degrees, and the length from this imaginary intersection point to the edge of 3. Okay, so that's another option. Takes up a lot more room, but you do have the option of calling it out this way. Okay, next. And once again, just want you to note that there is space between the 2 and the x, which signifies by, so 2 by 2. If there was no space between the 2 and the x, then that would indicate 2 places, or 2x, right, when you're talking about quantities. So to avoid making the mistake of assuming that it's 2 places, we put a space and a space, so we know it's 2 by 2. Next slide. Okay, so let's practice our drafting again, how to place and call out dimensions, or how to correctly label dimensions and use symbols. Okay, so right off the bat, we can see that we should avoid using words. Again, this was acceptable 50, 40, 60 years ago, but now, in the last few decades, we got away from using words. Instead of counterbore, we'll use the U shape to define a counterbore hole. So here we have a counterbore hole. And the depth, instead of using the word, we're going to use the downward arrow. Okay, another example of using symbols is we don't want to use words, right? We don't want to say 2 places. This is the old way of calling it out. Another way would have been 2 PLC or 2 PLCS, indicating 2 places, meaning there's 2 holes, right, with the same measurements. So we would have to replace this with 2x. We would play 2x right in front of the diameter 12 to indicate that there are 2 holes with the same dimensions. Okay, another thing to point out here, again, there's 7 mistakes. Forgot to mention there are 7 mistakes in this drawing. Another mistake is we're missing spaces here. So the 2x with no space tells us that there's 2 chamfers. Then we should have space 3 space x space 45 degrees. So that'll tell us it's 3 by 45. So from an imaginary intersection point to this point, it's 3 units with an angle of 45 degrees. Again, the 2x tells us that there's 2 chamfers. Another thing is we want the leader to be floating upward. So we want the text to be floating upward and the arrowhead pointing downward. So even though this is correct placement, it still looks better if it's floating and pointing downward. Okay, other mistakes that we see here in this drawing is when you call out a circle dimension for this, in this case, a circular hole, we do use the diameter symbol. But when you're dealing with an arc, we call it out with the radius. So this should be radius 15. So the diameter across is 30, but since we're calling out an arc, we're going to call it from the center to any point on the arc, which is half of 30. Half of diameter 30 is 15. So we're going to use R15 instead here. Okay, another mistake that we see here is this dimension of 10. Remember, we are not allowed to dimension hidden features. We can place the 10 up here, right? We can place the 10 up here, and that'll give us the center axis of the hole. Okay, once again, we are not allowed to dimension to a hidden feature. So here we have this counterbore hole. This dimension of 70 should be up here in the top view. We do not dimension hidden features, but here it's seen. We can physically see the counterbore hole. So we would place the dimension of 70 here. Okay, another mistake that we see here is maybe not a mistake, but that we are missing is we're missing the location for this radius. Now we do have a radius here, but we don't know where this point starts. So either we need to come in and place a dimension here, or we need to put a center mark and dimension the location of that center mark with a horizontal dimension. Okay, another, even though this 90, it's not incorrect to dimension this 90 to this line, but here we don't see what this line is doing when it clearly here we see that there's a step. So the 90, even though it looks good here in the group with the group of dimensions, it looks cleaner if you place it in the top view, dimensioning from this wall all the way to this side. So that'll give us a dimension of 90 in the top view. It just looks cleaner. You can leave it here, but it just looks better in the top view. Okay, so any other mistakes? I'm gonna say I think we got them all. Now we'll find out on the next slide. So let's look at the mistakes on the next slide. Okay, so let's look at the first mistake. And yes, we need to replace words with symbols. Again, counterbore, depth, places. We're gonna represent it with symbols and shorten it, and it'll take up less room. Okay, we forgot the spaces between the 3 and the X and the 45, telling us 3 by 45, which is a chamfer. And it's better if we angle up the leader, place it up here, pointing downward. Okay, next mistake is the dimension of 90 looks better in the top view. We can see that it's dimensioning a step. So let's place the 90 units in the top view. And again, we also caught the radius mistake. You do not dimension an arc with a diameter, you do it with a radius. And once again, we do not dimension to hidden features. So the 10 and the 70, which are both dimensioning to dashed lines, hidden features, should move up to the top view where you can physically see the object lines. And finally, we need to be able to locate the center of this arc. So we either have the option of dimensioning with the horizontal dimension from the edge to this point, but it looks cleaner if we do it with a locating the center of the radius. So with the little tick mark, indicating the center of the arc. Okay, now let's look at the correct drawing on the next slide. Okay, so here we see the drawing correctly dimensioned with symbols, right? And not with words. We have the chamfer dimension floating upward and pointing downward. And the 2x tells us that there are two chamfers. Notice there's no space between the 2 and the x, letting us know this is a quantity of 2. And then we put space, 3, space, x, space, 45 degrees. So this tells us the size of the chamfer is 3 by 45. And once again, we have the hidden features. The 10 and the 70 were down here in the front view, dimensioning the hidden features, which we're supposed to avoid. If we can, and we can here, we can place it in the top view, the 70 and the 10. And we also have the 90. The 90 looks better in the top view because we can see there's a step here. Here we can't really see what the line is doing, but here clearly the object line tells us there's a step. So it looks better to place the 90 in the top view. And also again the arc. We dimension an arc with the radius and a circle with a diameter symbol. And we also need to locate the center of the arc. There it is. Here are the dimensions, locating that center point of the arc. And I think we got them all. Next slide. Okay, so how do we choose dimensions? Choose dimensions based on function first, then manufacturing. So when we're talking about function is, what is the function of the part? How is the part going to be assembled with other parts? How is it going to mate with other parts? Are we going to bolt it down, clamp it down, or a combination of all? Are we going to weld it on? And also, how are we going to make the part? How is it manufactured? So this is what you need to take into consideration when dimensioning a part. When you're first starting off, it's very confusing. It takes a while to get used to it. If you have access to drawings or an old drafting book, especially the old drafting books from 30, 40 years ago, they always give great examples of how to dimension a part. Next slide. Okay, so this is what a typical drawing looks like. This is actually an actual drawing I created a long time ago when I only had about a year, maybe 2 years of experience, and I can already see mistakes. So we have front view, side view, top view. So one of the mistakes I see right off the bat is, notice how this leader is floating upward. I should have done the same thing with these other leaders here. Should have had them floating upward. And yes, it would have probably been crowded by these dimensions. So that's one excuse I can use. The reason they're floating downward is because these were in the way. But if possible, move them upward. It's still correct if you leave them the way it is. Okay, another thing you see in a drawing are tolerances. So inside the title block, you'll see what tolerance are you using. So the machinist, first thing they'll look at is, okay, they see the dimensions, but are these inches? Are these millimeters? So quick way to find out is just look at the title block. Unless otherwise specified, all dimensions are in inches. Okay, so 99% of the time when it comes to mechanical drafting in the United States, we're going to be using either inches or millimeters. If you're doing architecture, most likely you'll be in inches. If you look at old drawings, they would use feet and inches. For example, 5 feet, 6 inches, if you're looking at architecture drawings. Now it's probably all called out just in inches. Okay, so anytime a machinist looks at a drawing, they want to know how much wiggle room they can have. So if they look at this dimension, it has 3 decimal places, 1.250. So they see 3 decimal places, so 3 digits behind the decimal. So they go down here, look for 3 digits behind the decimal, and this will tell them, hey, you can be off by plus or minus 10 thousandths. A hair is about 5 thousandths, so this is double the width of a hair. So here you're telling the machinist you can be off by 2 hair thicknesses in either direction. Now again, I'm looking at my mistakes. This is too tight. I should have used 2 decimal places. 2 decimal places is about the thickness, or I should say 0.03 or 0.030 thousandths. It's about the thickness of a credit card or an ID card. If you only see 1 decimal place, then you can be off by 0.1, which is the same as 0.100 thousandths, which is about the thickness of a compact disc, or I should say 2 compact discs. Compact disc is about the thickness of about 50 thou, so 100 thou would be 2 compact discs. Okay, so another thing we see in a title block is what projection are you using? So again, in this class, we're only going to stick to third angle projection. If you were looking at a first angle projection, this cone shape would be over on the left side. Again, in this class, we're only going to stick to third angle projection, and this is the symbol for third angle. And again, this is your typical title block and border. Front view, top view, side view. Again, you try and group your dimensions together. You try and keep the dimensions between the views. And you try and avoid having dimensions by themselves on the outside. Here we have an isometric view. And here we have the revision block. So when you first release a drawing through document control, it gets processed, dated, signed off, everybody signs off, your supervisor, etc. Document control will sign off, and it's an official document, so think of it as a contract. Now if a few weeks later you want to change the diameter of the hole, so here we have a 0.59 diameter hole, it appears. So if you wanted to change it to a larger diameter, then you would say, okay, notice we have NC. NC is the original, which means no change. You could also use a dash or IR for initial release. So once we make a change, we would now go and use the alphabet and start with the letter A and a brief description of what you changed. Diameter 0.59, change to 0.65 diameter. Look at zone 6B. So this is letter B, this is letter 6. So you tell them at zone B6, look in that area, look for that dimension. So this dimension now has been increased, or the diameter has been increased. And then at the end you have the date of the change and typically the initials. Then it gets processed and released again through document control. It's a big deal when you have to do this again, but it's part of the contract and you need to properly go through the process of releasing it. Next slide. Okay, so you have to always call out which type of units you are using in your drawing, as we pointed out in the previous slide. On drawings where all the dimensions are either in inches or millimeters, the following notes should be used. So we saw it in the title block. Unless otherwise specified, all dimensions are in millimeters or inches. So you're not going to label each dimension like the one that you saw, like the dimensions that you saw in the previous slide. You're not going to label every dimension with 1.25 inches, 0.59 inches. You do not include the units because it's already in the title block. Now it's very rare, but once in a while you will mix millimeters with inches. So on our previous slide, we were dealing with inches. So all the dimensions are in inches because it told us in the title block that all dimensions are in inches. It's very rare, but once in a while you will create a drawing where you have all the same units. For example, all our inches, all the dimensions are in inches, but there's this one hole with a special size diameter, and the part that inserts in that hole, that part only came in millimeters. So if you went to a hardware store or went through a catalog of a hardware store, whether it's McMaster, Carlane, or your local hardware store, and the part you were looking for only came in millimeters, then in that case you would call out the dimension. Let's say, for example, 5.0 and mm for millimeters. So you would call out the abbreviation of the units if it didn't match the units in the title block. Next slide. So once again, this is the symbol for third angle projection. But if you're dealing with millimeters, another way to distinguish from inches is to use SI. Okay, so SI will tell us that we're using the metric system, in this case millimeters and third angle projection. If you don't see the SI, then most likely it would be in inches and not millimeters. Next slide. And just to recap, what is first angle projection? So if you're using first angle projection, which we don't use in this class, then the cone would be pointing in the other direction. So see the nose, instead of pointing inward, the nose is pointing in the other direction. So this is the symbol for first angle projection, which we're not using in this class. So once you identify the front view, for a first angle projection, you grab the player, the athlete, by the back of the helmet and swing 90 degrees. So this would be your left side view. This would be your right side view. So again, this is first angle projection, which we're not using in this class. Next slide. So for this class, we're only going to use third angle projection. So this is the symbol for third angle projection, inches. Okay, so notice the cone now is pointing inward. Here's the nose of the cone, and here's the nose of the side view. And this will tell us we're looking at third angle projection. So the difference between this one and the previous slide, which was first angle, the difference is you identify your front view, and this time the player messed up, so you grab the player by the face mask. So the coach will grab the player by the face mask, the player that just dropped the ball and caused the fumble. Grab the player by the face mask and swing 90 degrees. Notice how the nose or the face mask is pointing inward. Same thing with the left side view. You swing left, and this is what you get for the side view. The face mask is pointing inward, nose is pointing inward. Okay, so this is third angle projection. Okay, let's look at dimensions with one decimal place, 2 decimal places, and 3 decimal places. Okay, so what's the difference between 1.0, 1.00, and 1.000. Okay, does the arrow indicate an increasing or decreasing in accuracy? So here we're looking at the red arrow pointing towards the right. So the first one is less accurate. The more decimal places you add, the more accuracy you're asking for. So if a machine shop sees 3 decimal places, they know that you want more accuracy. So 3 decimal places, look in the title block, you can say, oh, I can be off by 0.010, which is 10 thousandths. Again, a human hair is about 5 thou. So you're telling the machine shop you can be off by 2 human hair thicknesses in each direction. So it can be 1.01 in one direction, or it can be 1 minus 0.01, which is 0.09. Okay, so that's pretty accurate. If you did not need accuracy, then you go with 1.0. So 1.0, you're telling the machinist, okay, 1 decimal place, I can be off by 0.1, which is 100 thou, 0.100. Okay, so 100 thousandths, that's the thickness of a compact disc, or I should say 2 compact discs. Compact disc for music is used, has a thickness of 0.050. Okay, so you can be less accurate with this one. If you want to be off by a thickness of a credit card, 0.03 or 0.030, same thing, then you use 2 decimal places and you'll go 1.00, and you're telling the machinist you can be off by plus or minus 0.030. That's about the thickness of a credit card or an ID card. Now when it comes to inches, if you don't know how accurate you're supposed to be, start with 2 decimal places. That's the most dimensions will be 2 decimal places. If you need more accuracy, then you'll go to 3 decimal places. Now if you need to fit a dowel pin, a cylinder inside of a hole, and you need tight accuracy, then you will go to 4 decimal places. It's very rare, but that's as close as you'll get, typically 4 decimal places. And we'll discuss tolerancing in a later chapter. Okay, next slide. Now, the more decimal places you use, 3 decimal places or 4 decimal places, for example, you're asking for more accuracy. The more accurate the dimension, the more expensive it is to manufacture. So if a machinist sees nothing but 3 decimal places or maybe 4 decimal places, then the machinist has to go slow to guarantee that the accuracy with those dimensions. If you're using 1 decimal place, like 1.0, then the machinist can go fast, machine the part at a high rate of speed, because accuracy is not important since you're only giving them 1 decimal place, such as 1.0. But if you're giving the machinist 1.000, 3 decimal places, then the machinist has to slow down and take their time to guarantee accuracy. So what it'll do is it'll drive the cost up. The more decimal places, the more expensive. To cut costs, it is necessary to round off fractional dimensions. And once again, the less decimal places, the cheaper the part will be. Only use accuracy, more decimal places when needed. Okay, so how do you dimension? Typically, you're going to dimension from a datum. So a datum is typically, for example, the base, so the bottom surface of this block. The bottom surface, that's a good datum to start with, and that'll be our primary datum. And the reason we use the base as our primary datum is because maybe there's a good chance this block is going to mount onto something or bolt on to another part, and it'll mate up most likely with the bottom surface. So this will be our primary surface. Also, when machining this part, it'll start off as a rectangular block of aluminum, for example. And when you set it on the machine, whether it's a Haas or a Fadal 3-axis machine, to machine the part, the base is going to be touching the table of the 3-axis machine. So base makes a good datum because it's going to be making contact with the table of the machine and most likely the part that it mates up to. Okay, how do we come up with our second datum? So we already defined our first datum as the base. So the second datum should be perpendicular to the first datum. So here we have a 90-degree angle perpendicular, and this back surface has more surface area than the third datum. So because there's more surface, we're going to call this one our second datum. So again, the base has more surface area. So that's our first datum. And then the back side, which is perpendicular to the base, has the second most surface area. So we'll call that the second datum plane. And the third datum plane is going to also be perpendicular to the base, our first datum, and to our second datum. Okay, so this has less surface area than the other two, so we'll call this our tertiary or our third datum plane. Basically what you're doing is setting up an axis. It's like setting up your X, Y, Z axis. Very similar. And again, they're all perpendicular to each other, 90 degrees. Okay, so most of the time features on a part are located with respect to a datum feature. Okay, next slide. So by setting up our datums, so we have our first datum, we can dimension from that bottom surface instead of that top surface where there's less surface area. So there's less surface area up here. So looking at the front view, we're better off dimensioning from the base and up. So here we have 65, 100, and 165. So we're dimensioning from this datum surface going up to 65, back down to the datum up to 100, and back down to the datum up to 165. Okay, so we're dimensioning from bottom up, and bottom up. Same thing with the side view. We're dimensioning from the base, our primary datum, dimension from the bottom up. And we're also going to dimension from the secondary or second datum. So this one also has a large surface area, not as large as the base, but it does have a large surface area, more than the front. See, the front doesn't have as much surface area as the back. So we're going to dimension from the back to the left. So right to left, we have the 40 and then 135 to left. Okay, so that was our second datum. And we also have our third datum. So in the front view, we're going to dimension from left to right because the left side has more surface area than the right side. So we're going to dimension left to right, 60, left to right, 200, left to right, 260. So that's how we dimension. Unless there's a feature on the part that tells you otherwise of how it functions or how it mates up to another part, we're always going to go from a datum. So first datum, bottom up, bottom up, bottom up. Second datum, back to front, and third datum, left to right, left to right, left to right. So this is the way we create our dimensions. We want to do it off a datum. Unless otherwise the part shows a feature that gives us a function or an idea of how it mates up to another one, then we may change how we dimension the part. Next slide. So how do we choose which surface to use as a datum feature? Well, one is the function of the part. So what's the function of the part? Another one is how does it mate with other parts? So the mating surfaces. And also you want to use a big enough surface to permit its use in manufacturing the part. So a good example is the base, the bottom surface, typically the largest surface of the part, which will be located and clamped onto the table of a 3-axis Fadal or Haas 3-axis machine. You'll clamp it down and you drill the features into it, like the pockets or holes, for example. Next slide. Okay, let's look at different ways of dimensioning. Datum dimensioning is preferred over continuous dimension. Okay, so the first one is showing us continuous dimension. Okay, so if you look at the base, and with dimension step by step, each step is 10 units in height. This is referred to as continuous dimension. and this should be avoided. The problem with continuous dimension is if the first step is slightly off, then that error is going to carry on to the next one. And if that one's slightly off, then the error of the first two steps will carry on to the next one. It's better to dimension from a datum. So in this case, the base. The base has a larger surface. So we guarantee more accuracy when we dimension from the bottom. So we're going to dimension bottom to top, 10 units. Then bottom to top, next step is 20 units. And once again, bottom to top, 30 units. So think of this as a strong foundation, a strong datum. And we have more accuracy when we dimension from that datum versus using continuous dimensioning, where if we have a step off by a lot, that will carry on to the next one and so on, causing the top step to be off even a lot more than dimensioning using a datum. Next slide. So here's an example of breaking the rule. So our first dimension of 15 is dimensioning from our datum to our first hole. So from the datum to the first hole, we have our first dimension of 15. And then our second dimension should also be from our datum. 15 plus 20, 35. Okay, so instead of 20, instead of using continuous dimensioning, we would use datum dimensioning and use 35, which is 20 plus 15. Okay, so this would be the correct way of dimensioning, using datum dimensioning instead of continuous, like it was shown on the previous slide. So why are we using continuous dimensioning in this example? Okay, let's take a look at the next slide for the explanation. Okay, so what's the reason for using continuous dimensioning when it comes to the two holes? Well, the reason is when it has to mate up with another part. So it could be bolts, it can be cylindrical dowel pins that go in the holes, and it has to mate up with another part with the same hole pattern. So the second part, when it's made, this dimension here of 20 is what's important. We want to guarantee that the two or the pair of holes match the pair of holes in the second part. So this is where we break the rule. Yeah, the first dimension will be off of the datum. So here we have the datum, 15 units from the edge to the center of the hole. But from there on, we'll use continuous dimensioning to guarantee that the hole pattern on this first part matches the hole pattern on the second part. Okay, so let's put this in practice. So we have a front and side view, and you can see right away some obvious mistakes. Again, we avoid doing continuous dimensioning. We want to do datum dimensioning. So we need to fix this. Another mistake that stands out is we're missing the diameter symbol, right? So instead of using drill, we would use the diameter symbol. Another mistake that we see here is we don't dimension to a hidden feature. So this 0.50 should go in the front view to locate the center of the hole with respect to the bottom datum. Okay, so any other mistakes? I think we got them all. Okay, so let's take a look at the next slide. Okay, so let's look at the first mistakes. Okay, so we have a mistake of 2 decimal places. So what it's telling us is that we should be using 2 decimal places. So anytime you start a part and you're dealing with inches, you don't want to use 3 decimal places. That's too accurate. So it'll cause the part to be more expensive. So let's use 2 decimal places and drop the third digit behind the decimal point. And also no leading zeros. So what does that mean, no leading zeros? Anytime you're dealing with inches and the dimension is smaller than 1, you do not use the 0 in front of the decimal point. Here we have another one over here on the side view. So when you're dealing with inches, you do not put a 0 in front of the decimal point. If this was millimeters, you would place a 0 in front of the decimal point. So that's one way to distinguish millimeters from inches. If you see a 0 in front of a decimal point for a number smaller than 1, then you know it's millimeters. But in this case, we're dealing with inches. So you do remove the 0 in front of the decimal point. And once again, since we don't need accuracy, we're going to get rid of the third decimal place for all the dimensions because we don't need the accuracy. Okay, next mistake. Use datum dimensioning. So it was mentioned, as it was mentioned in the previous slides, you avoid using continuous dimensioning. So we're going to use datum dimensioning to create our dimensions here. Next mistake. We need to use the diameter symbol. Oh, and one more thing, we do not use fractions. Now, fractions were used decades ago. Also in architecture, they used to use fractions: 1/2, 1/4, 1/8, 1/16, 1/32, 1/64. But because it's difficult to add and subtract fractions, everything was turned into decimals. So it's to avoid mistakes when it comes to adding or subtracting fractions. So also in architecture, they're removing the fractions, and in the last few decades, we've been going over to decimal places. Okay, so let's look at the next mistake. And again, you don't dimension a hidden feature, so we need to move this dimension over to the front view. So here's the correctly dimensioned drawing, detailed drawing. Again, a detailed drawing is a drawing of a single part. So we have our front view, side view, and here it is. We have datum dimensioning as opposed to continuous. 2 decimal places, so everything is at 2 decimal places. The area where you will see 3 decimal places is typically a hole. So depending on what type of hardware, whether it's a dowel pin, a bolt, then you may increase this to 3 decimal places, maybe 4 decimal places. If you don't know what type of hardware is going inside the hole, then you leave it as 2 decimal places. So again, we want everything in 2 decimal places. Also, since we're dealing with inches, we don't put a 0 in front of the decimal point. Okay, if it was millimeters, then we would place a 0 in front of the decimal point. So by removing the 0, we're telling whoever's looking at the drawing, we're telling them that this is in inches. Again, we don't have the 0 in front of the decimal point. We have the diameter symbol, but not a 0 in front of the decimal point. So this is with any dimensions lower than 1. Drop the 0. And this is only 4 inches. Okay, and also we don't dimension a hidden feature. So here's the 0.50. Instead of placing it in side view, we place it here in the front. And we go from small to large. So 0.50, 1, 150. Same thing with these dimensions. We start with the smaller dimension and work our way to the larger dimensions. And we do want our text on a liter to be floating up towards the right and not floating downward. And we always want the arrowhead pointing towards the center of the circular hole. And again, it's okay if you cross extension lines. So extension lines can cross each other. In this case, we couldn't avoid crossing the leader. One thing you can do, and we'll learn this in AutoCAD, is to create a break. You can create a break to avoid crossing a leader, or you can just leave it the way it is. Next slide. So let's practice. How would we dimension this part? So we have a front view, top view, side view. And again, the rule is you try and group dimensions between the views. And you try and dimension off of datums like the base or the larger surface. Okay, so once we identify our datums, then we can go ahead and start placing dimensions. So now that we've identified the datums in the top view, so this datum, this has more surface area than the opposite side. Same thing with the back surface, that has more surface area than the front. So we've established our datums and we dimension from them datums. So from this red datum, we're going to go right to left, right to left, right to left, giving us 20, 55, and 82. And this group of dimensions will dimension off the rear datum, the back datum, dimensioning forward from back to front, giving us 35, 40, 70. And we have this lonely dimension. Again, we try and group them together, but it would create a long extension line, so it's better to leave the 50 here by itself to avoid using a long extension line if we placed it here between the 40 and the 70. Okay, let's take a look at the next view. Okay, the front view. Again, the base, that's a good datum, a lot of surface area, and we also identify this as a large surface area. So for the green datum, we're going to dimension from bottom up, giving us 50 and 75. And for our horizontal dimensions, we're going to go off of the right side, which has more surface area than the left side. Okay, so we're going to dimension from right to left, right to left, right to left, giving us 30, 100, and 125. So that's how we dimension. We identify our datums and dimension off of those datums. Okay, so let's identify our datums on this detailed part. So we have our front view, top view, and side view. Okay, so for the front view, we can use the base as a datum, and we can use this back surface as a datum. And finally, we can use this surface, which would be this surface here, as our third datum. So primary datum, secondary datum, and tertiary datum. Okay, so now let's look at the next slide to see how we would dimension this detailed part. Okay, so from the front view, we've identified this as our datum. So here's our dimension. From this lower datum, same thing here, it's the same datum, our primary datum that we see in the front view is also here on the side view. And we dimension from the bottom up, same thing with the 10, bottom up. Okay, so now for this datum, we're going to dimension from the back forward. And we don't have an overall dimension. That'll be covered in the top view. Okay, so then we have our tertiary datum, and we're going to dimension from back to left. And the overall dimension here will be covered by the top view. So let's take a look at the next slide. Okay, so we don't have an overall length for the front view. So we can actually calculate that overall length. This overall length, it's actually 45 plus 18. So 45 from the datum to the center of the hole, we have 45. And we have a radius of 18, which is from the center to any point along the arc. So by simply adding 18 plus 45, that'll give us 63 overall length. Now we're duplicating dimensions. So the 63 has to be placed in parentheses, meaning it's a reference only. So a machine shop, an inspector, when they see this drawing, they know that the 63 is reference only. And we're telling them that the 45 and radius 18 is more important. So typically when you have a situation where you have the center of a hole is more important than the overall length, then we call out the radius and the length from that center point to the datum. Okay, next slide. Okay, so let's identify our datums for this detailed part. So the front view, obviously the base would make a good primary datum. A secondary datum would be this side as opposed to the back side. There's more surface area here on this side. And also this side has more surface area than this side. So this would be our tertiary datum. Once again, primary datum, our secondary datum, and our tertiary datum. So let's take a view at the top view. Okay, so we have our tertiary datum. So we're going to dimension left to right. So we have 12 to the center of this shaft or cylindrical solid. And then our dimension to the center of the circular hole. And finally the overall length of 75. Okay, so those are our datum dimensions off of the tertiary datum. And we have our secondary datum. So we're going to dimension from front to back for the depth. So from front to back, we have our 15 units. It happens that these two holes happen to be on the same line horizontally, so we can use one long center line. And finally, the overall depth is 30. And don't forget, if you're dimensioning an arc, so here we have what's called a fillet, a round, an arc. We're going to dimension it with a radius. So here we have a radius of 10, and the arrowhead is always going to point to the imaginary center point of the arc, which is somewhere around here. And we also have the diameter of the hole. So if it's a full circle, we go with diameter. Okay, so full circle, diameter of 10 is the size of the hole. Notice we did not dimension the diameter of this circle, and it's because it's a solid. So if it's a cylindrical solid, in this case a shaft, a round shaft, then we don't dimension the circle, we dimension the rectangular view. Next slide. So here we have the diameter of the shaft or the cylindrical solid of diameter 15. So again, here we have a circular shaft, a solid, so we do not dimension the circle, we dimension the rectangular view. If it's a circular hole, as you can see here, the hole goes all the way through, then we dimension the circle, diameter 10. And if it's an arc, we use radius and not diameter. Okay, once again, we have our primary datum. We have our overall height, right, of 30, and the step is 15, so we dimension from bottom up, bottom up. And we don't need to dimension the side view. All the dimensions are taken care of in the front and top view. Okay, so now let's take a look at this part. We have a detailed part. Let's identify our datums. So a good datum is the base. This can be one of our datums. We can actually consider the back surface our primary datum because there's more surface area than the base. But maybe it was manufactured with this mating up to the 3-axis table. Okay, so this is a good datum. This is a good datum here. And when it comes to the front view, the left or the right, they're identical when it comes to surface area. So it doesn't matter if we choose the right or the left. In this example, the author chooses to use the right side as a datum instead of the left. Okay, next slide. So let's take a look at the front view first. So we have the base as a datum, so we're dimensioning bottom to top, bottom to top, bottom to tops, and that's how we get 20, 35, 52. And we also have this dimension of 5, which looks better in the side view. So the dimension of 5 units, we could have placed it here with the other group, but it's not clear what this line is doing. But here we can see it's a step, so it's better to leave it on the right side view even though it's by itself. We also have this wall thickness of 8, so we're dimensioning from back to front, and we're missing the overall depth, so that will show it in the top view. But before we go to the top view, let's take a look at the front. We have a chamfer at 45 degrees. Okay, so how is this chamfer located? So we go over here to this side. So we have a dimension of 35, angle 45. We know this is 45 because this is 45, and the 2x tells us that we have an angle of 45 degrees at 2 places, 2 locations, 1, 2. So the chamfer here, we could have called it out differently. We could have just subtracted 35 from 52, which is 17. So we could have called it out differently. We could have said, hey, we have a chamfer here of 2 of them. So 2x would tell us that there's 2 of them, space. And we would say it's 52 minus 35 is 17. Space by space 45 degrees. So that could have been an option. But here the drafter decided that this dimension was more important than the 17. So instead we dimension it this way, the longer way. So 35 from this starting point of the chamfer to the datum. And we have the 45 degrees. and the 2x indicating that it's 2 places. Okay, let's take a look at the top view. Okay, so we have the top view, and using datums, so they use the rear surface, which is the surface with the most surface area, so this is an important datum. And we have the overall depth of 28. We could have placed the 28 here. And we have the 18. So 18 is from the back datum to the center of the hole. And you don't have to put 2x indicating it's 2 holes, the distance from the back surface to each hole. The center line will take care of the 2x, so we don't need to place 2x space 18 to indicate that the dimension accommodates 2 holes, because they share the same center line, so we can leave out the 2x. Okay, we also decided to go with the datum on the right hand side, so that's how we come up with 35. From the right datum to the center of the hole. Same thing with locating the first hole. Right datum, center of hole, right datum to the second hole, and finally the overall length of 70. Notice here we didn't use continuous dimensioning. Instead of the 58, we could have used continuous dimensioning. So take 58, subtract 12, that'll give us 46. Now we could have used 46 instead of the 58, but since the 46 was not used, that tells us that the hole pattern is on its own. It doesn't mate up to another part with the same hole pattern. Okay, so here the 58 is more important than the 46, so we'll just use datum dimensioning versus continuous. And we have 2 holes, so the 2x tells us that there's 2 holes, space, and a diameter of 7 for each one. End of slide. Okay, class, this is the end of this presentation. And in Chapter 8, the next chapter, we will be dimensioning in AutoCAD. See you in the next presentation.